In this lecture, we continue to discuss about the flow physics and how do we connect it with the flow computations, and then we will also look forward to different steps involved in flow computations. Continuing from where we left last time, we now see finite wings. So, you can see a picture of an aircraft close to the ground, and you can very well figure out that it has a swept tapered wing. So, we are talking about finite wings, and of course, when we simulate, then either we can begin simulating it by having a cleaner configuration where the engine is not there, and then adding it on, and then also solving it in proximity of the fuselage and so on. So, there are different levels of sophistication that you can bring in gradually into the flow computations. We had earlier discussed the concept of wing tip vortices with respect to finite wings, how it develops and trails behind the aircraft due to the pressure imbalance between the lower and upper surfaces, because of which the flow tends to roll up from the lower to the upper surface, and as a consequence there is a velocity distribution near to the wing tip of this kind. So, when flow computations are performed, you can see results of that over here, and you can also make out that both leading edge and trailing edge high lift devices have been deployed here. So, it is similar to a situation like this, and then here are some instantaneous streamlines which can give you a feeling that the flow is tending to roll up from the bottom, and it is also creating a kind of a spiraling flow downstream, which is because of the roll up and its consequent advection into the wake of the wing. And then this is near to the root of the wing, where there is a fairing, as you can see on the aircraft also there is a fairing in this region, so that the wing meets the fuselage, and in that region the flow behaves smoothly, secondary flows are minimized, etc. So, that there are less interference effects and additional drag is minimized. And here additionally you can figure out that apart from the wing tip region, the flow tends to be behaving smoothly, it is not detached, it remains attached all the way through to the flaps, and therefore, the high lift devices are nicely getting the flow to move over that large camber that is created, and an augmented surface area that is created, which generates more lift. Very often these flows are also turbulent in nature, and we discussed about enhanced momentum exchange in turbulent flows because of the fluctuations which occur in such flows, and that makes the boundary layer more robust. So, if you look at the boundary layer, typically it will be a more robust boundary layer with a fuller profile close to the wall, and therefore, that enables the flow to remain attached even under more adverse pressure gradients. So, of course, pressure gradient is handled more efficiently over here by making use of the momentum injection that is happening through the gaps which are created between the high lift devices and the main wing. But a turbulent boundary layer also enhances the robustness of the flow. So, these are the regions through which momentum augmentation is occurring in the boundary layer. So, this is one region, one gap, this is another one. So, through this more momentum is getting into the boundary layer and energizing it. Here we look at a more complete aircraft or spacecraft configuration over the next few slides. So, here the same high lift devices on the verge of takeoff, let us say, can be seen in a three-dimensional sense. So, you can see the complete wingspan and the high lift devices deployed. Additionally, you have the spoilers deployed over here, which can help you to decelerate quickly after it just touches down by augmenting the drag. So, these are spoilers which can increase your drag after the aircraft touches down. These are winglets which are often deployed at the wing tips, and they help you to reduce induced drag. So, in flow computations you can see the winglet being modeled over here. So, winglets are found in most of the modern transport aircrafts because they reduce the induced drag of the finite wing. So, you see a large passenger aircraft somewhat similar to the A380, the Airbus A380, that is the double decker with 4 engines. And if you look at the flow field, it remains nicely attached to the wings. It also flows smoothly past the horizontal tail, the vertical tail, and the fuselage regions also. Separation of course is created near the landing gear, some part of the trailing edge of the engines, and thin wakes formed from the narrow lifting surfaces which are essentially streamlined. You can also observe the flow turning here if you follow the streamlines carefully. This is a closer look at the flow. So, you see how the flow moves past the different surfaces, the adjustments to its direction, etc. If you look at the military aircrafts, they are much smaller ones, they fly much faster, they are also very agile aircraft. They have to make very rapid maneuvers, and because of which they are usually built much stronger and they can sustain higher Mach numbers, for which structurally they have to have much more stiffness as well. Additionally, the payloads which are there on the military aircrafts are of a very different kind for defense purposes, and from the aerodynamic perspective, you would often see the use of the delta wing, low aspect ratio delta wings, and we have studied about delta wing aerodynamics to some extent. You may recall this diagram where we talked about the flow rolling up from the sharp leading edge of a delta wing and then making it an efficient lifting surface up to a large angle of attack, and that large angle of attack is very important for these kind of aircrafts because they have to make maneuvers which often involve large angles of attack. And you can of course make out that these are low aspect ratio wings. Here you can see the streamline patterns behind the aircraft, and they look quite complex. There are flow features behind the payloads also in addition to the wing. As far as space vehicles are concerned, we have an example here. It is basically the space shuttle, which is now no longer in service. the NASA space shuttle. So, this is the orbiter which used to carry the human and experimental payloads to space, and this was the main tank with 3 main engines at its base. So, this main tank used to have liquid oxygen and liquid hydrogen. That means, these are used for powering cryogenic engines, and then we have the booster rockets which carry solid propellants. So, these were some important elements of the space shuttle, and the orbiter was a reusable vehicle which would come back to the Earth's atmosphere after the time it spends in orbit. So, this is also a re-entry vehicle which is capable of encountering very high Mach numbers, which produces large heating etcetera when it re-enters the Earth's surface. So, you can see contours of pressure over here, and here are the jets which are emanating from the rockets, and you have learned quite a bit of the high speed aerodynamics which will help you to explain quite a few features over here. If you look at the flow features here, which are formed near to the tip of the main tank, you can figure out that there is a kind of a bow shock structure over there. There are expansion fans in regions like this, and then there is also flow through a nozzle in a region like this, which you can identify from some of the aspects that we learned in high speed aerodynamics. You also remember having learnt about the shock wave boundary layer interaction. So, you can imagine that there are regions in this flow field where such interactions are possible. For example, if you zoom into a region like this, so there would be a shock which will be formed near the nose of the booster rocket, which can go and impinge on the boundary layer which is formed on the main tank. So, such a situation is reflected here through the incident shock, and it is found in many other regions of the vehicle here, because it is a complex geometry, and there are lots of locations where such interactions are certainly going to happen, but the detrimental effects of such interaction have to be minimized. So, you need to always keep in mind that you cannot eliminate all of it, but you have to minimize the detrimental effects. Of course, we also discussed the existence of Prandtl-Meyer expansion. So, we have been seeing more instances where flow computations can be well explained from the physics point of view, which you already have learned about. And then most of the time we have been spending on external aerodynamics, flow past bodies. So, they were basically flowing over bodies or past bodies, but there could also be flows of interest in terms of aerodynamics, in terms of aircraft applications, where flows happen internally. So, these are essentially internal flows, which we are currently looking at in this slide. And in internal flows, the flow would move through certain passages, certain enclosures, etcetera. So, here you see flow through turbomachinery blade passages like axial compressors and turbines, which are deployed in aircrafts. This is a more complete engine where you can understand that a flow is coming into the first stage compressor of the gas turbine engine of an aircraft, and then it goes through compression, then it goes into the combustion chamber where fuel is mixed and it is combusted, and then very hot gases are expanded through the turbine. So, there could be computations of this kind which uh, deal with internal aerodynamics. And when you take a closer look at, say, how the flow is mixing with the fuel, how it is turning around, purposely you are creating some recirculation pockets so that you can stabilize the flame and hold the flame in such regions. So, all that is done by having a very detailed flow simulation of the combustor. So, this is a typical combustor of gas turbine engine. You essentially have a chemically reacting flow, a high temperature flow, and then you also have to take care of the thermodynamics aspects of such a flow. Also, you have to look at the equation of state for such a situation, etc. In the cabin of a transport aircraft, a passenger aircraft, you can look at the airflow that occurs from the ventilation system. So, that involves passenger comfort, etc. So, that is also a simulation of airflow, which we are talking about over here. So, these are other applications where you do simulations and you try to understand the movement of airflow through different devices and how it affects the performance of such a device. Now, let us try to come to a more formal examination of the procedures which are involved when we do flow computations. So, when do we use computational aerodynamics or computational fluid dynamics? If that question is posed to you, then the answer to that would be that we do not have a straightforward theoretical solution available for such a problem. So, it may not be existing because of several reasons. One of the reasons could be that the problem is too difficult as it exists in reality, which can be modeled with available mathematical tools. Also, it could be because of the domain or geometric complexity of the problem, because of which an analytical or theoretical solution is not available. The other problem is that from an experimental angle, if you want to really pursue such a problem, you may not have the facilities to do it, or you may not be able to create those situations realistically in the available experimental setups. So, these are reasons why we actually go for computations. And then once you decide to go for a computation, what are the advantages you have? The primary advantage is that you can have a lot of details in terms of the flow field, both in space and time. So, that is what is called as a high resolution. You can resolve the details in space and time to the extent that you want within the computational restrictions of today's technology, but that is at a quite high level. Therefore, the resolution is really high, and then flow parameters can be changed much easily without much additional expense or trivial additional expense, which is extremely difficult to do in experiments. So, if you really want to change flow parameters, you may actually have to build new models, you may actually have to move to a different wind tunnel facility, which makes it extremely expensive and difficult to perform. So, such conveniences are available in computations. Now, if we try to answer the question that what are the steps involved in performing such a CFD simulation of a flow problem, then these are broadly the steps that one looks at. So, it begins with definition of the problem and the objectives that we have in mind for performing such a CFD simulation. So, the better you define the problem, the better you can identify the objectives, the better you can take the next few steps, because this has a very close connection with the governing equations that you would be choosing. Once you define the problem, once you decide what are the objectives you have in mind to fulfill, the governing equations basically answer that question. And governing equations are again based on approximations. So, you in the process are also identifying this question and answering it, that what level of approximation are you able to meet through those governing equations. Once these two steps are taken, you have broadly addressed both the physics and the mathematics of the problem, so that you can get deeper into it and then focus more on the computational activity. So, the next few activities are essentially the heart of the computational activity, but the backbone of that activity lies in the first two steps. If we do the activities involved in the first two steps correctly, only then can we expect favorable outcomes coming from the next three steps. So, the next three steps essentially involve solution of a particular governing equation, which can be a say a partial differential equation, a single partial differential equation, or it could be a system of partial differential equations. And then we do not have an exact solution of it most often, and therefore, we have no other resort but to numerically approximate it and solve. Therefore, we cannot solve it at an infinite number of points both in space and time. We have to discretize the domain, and we have to reduce it down to a kind of finite dimensional problem. That is why we discretize a particular domain that we define for ourselves into a finite number of bits and pieces, and this is essentially what we mean by grid generation. Here, in terms of grid generation, we mean that the spatial domain is being broken down into bits and pieces. For example, if you have a regular say Cartesian axis fitted square or rectangular domain, then you might decide that you will run few lines like this parallel to x and few lines like this parallel to y, and thereby you would discretize the domain into 16 number of small pieces. So, that is basically the process of grid generation. So, you are breaking the domain into smaller pieces, and then you decide to solve the problem on those smaller pieces. Now, how you solve it ultimately on the smaller bits and pieces depends on the method of solution of the governing equations, which are most often partial differential equations, and these equations of course, from a mathematical angle can be solved based on a suitable set of initial and boundary conditions. And then we choose from a few standard methods and deploy one of them to solve the problem. So, few of the standard methods are finite difference method, finite volume method, finite element method, for example. And once you apply this any one of these say three techniques to convert the governing partial differential equation or equations into an approximate form, most often they form a set of algebraic equations. So, you basically translate the problem from a PDE form to an algebraic form, and that happens through use of one of these techniques. So, once you convert it into algebraic forms, there are efficient techniques of solving them. However, as you solve them, you have to address issues of stability and accuracy of the numerical scheme again, which of course is already taken care of when you have converted the partial differential equation into its algebraic form. So, when you make the conversion, at the time itself you have to take care of these issues, so that when you attempt the numerical solution, it remains stable and it does not become an unstable process which crashes finally without yielding a satisfactory solution. Also, whatever solution you get is reasonably accurate. So, such things have to be kept in mind while you go through this process. And we remember the previous process which we did was that of discretization. So, that is often called as a pre-processing step. That means, you are actually making an arrangement in the beginning. That is why we use that word pre-processing, and then the heart of the computation lies in the flow solver step. Because the grid generation comes before the heart of this computational activity, which is the flow solver step, we often call it by the name pre. and what follows after the flow solver step is therefore a post. So, we have a post processing step. Once this step gives us a whole lot of numbers, essentially numbers in the sense they could be essentially decimal numbers with different precision. It could be single precision, it could be double precision, etc. And then you would have solved them over a large number of such bits and pieces, and therefore, there would be a large number of numbers which will come out of the numerical process. At that time, you would have to represent those numbers by suitably deploying some graphical tools. All right. So, once you plot them, you have a graphical representation of those numbers. So, you are looking at the results now, you are visualizing them. So, we did a lot of visualization of such data in the last several slides, and we realized that once we look at those numbers through such graphical plots, they help us to analyze it better, because even by looking at such result, we can have a much better idea about the flow physics. And then it is not enough if we just get some numbers and we are able to plot them, but we also need to validate them in some manner. That means, there need to be some test cases which we have to run and make sure that the results are reasonably good compared to some standard cases which are already available in literature. So, that step where we try to compare our results with available results is what is called as validation. So, these are steps which are involved in the post processing level. So, we are once again recalling that in the core part of the computations, we are talking about a discretization step which is called as pre-processing. We have solution of the governing partial differential equations which are often in an algebraic form, and because you are solving it over a large number of small domains, subdomains which have been created through the discretization process. Therefore, there will be a large number of algebraic equations which you have to solve, and often solve them simultaneously. So, you may actually have to use matrix based approaches to solve them. Once you solve them, you have a large solution set which are essentially numbers. You then have to plot them by using some graphical tools, and then once you see the numbers displayed through some visualization by using contours and colors and so on, you should be able to interpret the results qualitatively to begin with, and then quantitatively. And when you try to do a quantitative comparison, then you need to have some test cases with which you try to prove the worth, the accuracy, the stability of the solution that you have generated. So, once you do that, the solution is validated, then your process is well proven, and then your results can be believed. So, these are more or less the main activities, the main steps that are followed in a CFD simulation. There could be somewhat simpler frameworks where not all of these steps may be involved, or you have a certain amount of simplification in the steps. One of such techniques we will discuss soon when we look at panel technique, for example. It is a slightly simpler implementation of these steps. So, we will begin with simpler models of that kind, and then we will move on to more complex equations like Euler and Navier-Stokes equations, where essentially all these techniques are actually implemented in totality. So, let us see what we discussed in this lecture. Let us sum up. We discussed further about connecting the theory with flow computations. We discussed about some finite wing, low aspect ratio, high angle of attack, delta wing applications. We discussed about compressible flow applications and so on, and also a little bit of internal aerodynamics. Further, we looked at the different steps involved in a flow computation. Thank you.